Yeah, hello everyone. Good afternoon. Am I audible and visible, students? Just give your answer here in the class status checking. I have launched a poll. Yeah. Am I visible and audible to all of you? Good afternoon, Pallavi. Very good afternoon. Okay. Good afternoon, Sneha. Okay, fine. So let me end the poll, okay? So I'm visible and audible to all of you, I think. That's great. So today we are going to start with a new chapter. Okay, so how many lessons we have completed? Can anyone tell me the number of lessons we have completed in chemistry? 3. Solutions, electrochemistry, and chemical kinetics, right? So those 3 lessons are physical chemistry lessons. All right. So the lesson which we are going to see today, which is called as coordination compounds, is an inorganic chemistry lesson. Okay, and this coordination compounds lesson has more weightage in your exams, so you have to concentrate much on this lesson, and you need to solve more number of questions. Okay, and this lesson is easy only. Okay, here we don't have much of calculation, so it will be easy. Since it is an inorganic chemistry lesson, it will be easy to understand, as well as it is easy to find out the answer. Okay, so you won't get the time consuming questions from this kind of chapters. Okay, so very easy, but it is important. All right, so let me go with the coordination compounds. What are coordination compounds? What are coordination compounds? So it is a, yeah, I will come to the answer for yesterday's question at the end of the lesson. I will tell you. Okay, Sneha, did you get the answer for that question? Just keep it with you. When I am asking that, you can tell. I have that in mind. I will do that at the end of the lesson. Okay, very good. Yeah, what are coordination compounds? It is a specific type of compounds formed by certain elements. Okay, so certain elements in the sense we can have a metal. Okay, or we can have an anion or a neutral atom. So that anion or a neutral atom, what it will do, it will come with a pair of electron and it will form the bond with the metal. Okay. So now this metal and the anion or the neutral atom will form a compound, and we call that compound as coordination compound or complex compound. Okay, coordination compound or complex compound. So now I am going to give you some complex or coordination compound in biological system. Okay, so the first example is chlorophyll. Chlorophyll is a coordination compound in which we have the magnesium as a metal. Okay, and the next one is hemoglobin. Here iron is acting as a metal, iron complex. And vitamin B12. Here cobalt is acting as a metal, and this is called as cisplatin, which is an anti-cancer drug used in the medical field. And here the central metal atom is a platinum. So it is a platinum metal complex. Okay. So all these are the coordination compounds in the biological system. So what we have a metal and we have an anion or a neutral atom which is coming with its electron to form the bond with the metal, and those compounds are called as coordination compounds. Okay. So now let's go for the introduction to this coordination compound. So in this topic, I have 4 subtopics for you. So the first is Werner's theory, and next we are going to study some terminologies, basic terminologies pertaining to the used in coordination compounds, and we'll study about the ligands and its classification, and at last we will study about how to name the coordination compound using IUPAC nomenclature. Okay, so all these things are going to get covered in this first topic of this lesson. So let's start with the Werner's theory. So this Werner's theory, you can able to see the scientist picture, right? So he is Alfred Werner, and he is the father of coordination compound, I can say, because he only first discovered the coordination complex in his lab. Okay, so he did an experiment. Now we will see that experiment that led to the Werner's theory. Okay, so what he did, first of all, he took 1 mole of a cobalt chloride complex. Okay, I'll give you the formula. So in this test tube, in one of the test tube, he took 1 mole of this cobalt chloride with the 6 ammonia molecule containing complex. And he added AgNO3 to this cobalt chloride compound. Okay, AgNO3 is another compound. Now he is adding that compound to this. So after adding this, he observed that 3 moles of AgCl was getting precipitated out. You know what is precipitate, right? Guys, do you know what is precipitate? Can anyone tell me what is a precipitate? Can anyone tell me what is a precipitate? Oh my God. None of you know the answer. What is a precipitate?
White substance.
Yes, substance which settles down, okay, at the bottom of the container is called as a precipitate. Okay, so here AgCl is precipitating out and yeah. So 3 moles of AgCl is precipitating out. Okay, means 3Cl from the compound might have combined with the AgNO3. That is the meaning. Okay. And secondly, what he did, he took the same 1 mole of the cobalt chloride salt, but with the 5 ammonia molecule, and he added the same AgNO3. And he observed only 2 moles of AgCl precipitating out. Means only 2Cl might have combined with AgNO3. Okay. Thirdly, what he did, he took the same 1 mole of cobalt chloride with 4NH3, and he added the same silver nitrate, AgNO3, and he observed 1 mole of AgCl precipitating out. So what is the meaning? 1Cl minus ion might have combined with AgNO3. And at last, he took the same compound, but you see the color. Color is different, no? One is green and the other one is violet kind of thing. And he added the same AgNO3 to that compound also, but again 1 mole of AgCl got precipitated out. So both of them have the same formula, but color is different for both. Means both are different compounds. I will tell you that difference in the upcoming slides. Okay, so don't worry about that. For now, you just keep all these things in your mind. In the first experiment, 3 mole of AgCl is coming out with the 6NH3, and if I am using 5NH3, 2 is coming out, and if I am using 4NH3, 1 mole of AgCl is precipitating out. Okay, so these are the observations he got from his experiment. All right. Now, next what he is doing conductivity experiment. So he is taking the same thing. He is going to do the conductivity experiment. So in the conductivity experiment, what is happening for the first compound, he is getting 1:3 solution conductivity. Means he is observing, he is having 1 cation and 3 anion in his solution. And for the second case, he is getting 1:2. So means 1 cation and 2 anion. And for the last two, he is getting 1:1 solution conductivity. Means only 1 cation and 1 anion is present. So this is the experiment he did. The conductivity measurements he did in his lab. Okay. So first what he did, he took these compounds and he added AgNO3 and observed the number of moles of AgCl precipitating out. And secondly, he is doing the conductivity experiment and observing 1:3, 1:2, 1:1 kind of a thing coming out. Okay. So from these two experiments, he is coming to some conclusions. So now let's see those conclusions, okay, of Werner's experiment. So he proposing the structure of the compound. So from in his conclusion, he will tell the structure of the compound also, the coordination compound. Okay. So first, what happened for 1 mole of COCl3 and NH3? What happened? We have got 3 moles of AgCl, right? And also we have got 1:3 electrolyte. And we said that we have only one cation and three anion. So from this, he proposed a structure for this compound. Okay, and the structure is CONH3 6 times 3 plus 3Cl minus. Okay, so if he puts 3Cl outside, then that is the reason those 3Cl which are there outside this bracket is responsible for the 3 moles of AgCl precipitating out. Okay, clear? And he got 1:3 electrolyte, right? So he had one cation and this is that one cation and these are those three anions. So this is one cation and three anion, 3Cl minus. So that's why we are getting the 1:3 electrolyte and this could be the structure of the coordination compound or the formula of the coordination compound which would be existing for this. Okay. And for the second case, for 5NH3, we have got 2 moles and 1:2 electrolyte. So what could be the formula? So 2 mole of AgCl precipitate means only 2 Cl minus is outside the bracket. Okay. So 2 Cl minus outside the bracket and 1 Cl is inside. Okay. And we have only 5NH3. We have only 5NH3. So that is occupying the complex. Okay. Coordination entity. So here we have one cation and 2 anion. So 1:2 electrolyte. Okay. And for the third case, we have got 1 mole of AgCl coming out and we have only 4 NH3. So what could be the formula? To keep only one Cl outside and one cation. This is the complex cation. So one cation and one anion. So 1:1. And for the last thing also it is same only. Right? Only the color difference will be there. I will come to that later. So here also we have only one cation, which is the complex, and this is the anion, one anion. So 1:1 electrolyte with 1 mole of AgCl precipitating out. So is it clear up to this? And he is calling these compounds as coordination compounds. Okay. So any doubt till this? Any doubt till this for anyone? If it is clear, type yes in the chat box. If it is not clear, just ask me. Yes. So everything is clear about the Werner's experiment for all of you, right? Okay, okay, very good. Thank you, dear students. Now, let's go for the postulates of Werner's theory. So postulates are very important. Okay, so far we have studied the experiments and the conclusions. Now, from this conclusion, he is proposing some postulates of Werner's theory. So, in the first postulate, he is saying that coordination compounds have two different types of valency. One is called as primary valency and the other one is called as secondary valency. Okay. So, primary valencies are ionizable and normally satisfied by negative ion, but secondary valencies are non-ionizable and are satisfied by negative ion or neutral atom. Okay. So primary valency is nothing but oxidation state and secondary valency is nothing but the coordination number. Primary valency is the oxidation state. Secondary valency is the coordination number and it is fixed for a metal. Okay. And the secondary valencies have different spatial arrangement for different coordination number. Okay, if the coordination number is 4, then the spatial arrangement would be different. If the coordination number is 6, then the spatial arrangement will be different. If it is 5, then the arrangement of atoms will be different. Okay, so we will study all these things in detail in the next slides. I'll take one example to understand this. I'll take one example. Which example? Okay, Let me take the same example. CONH3 6 times Cl3. Okay. So this is the example. So primary valency means oxidation state. So what I have to do, I have to find out the oxidation state of this metal atom, which is cobalt. Okay. So let me take this as X. And for NH3, I have to put 0. I will tell you how to find out the oxidation state for a metal atom in the later slides. So don't worry, okay? For now, you just keep in mind that NH3 is a neutral compound, so it is taking the charge 0. And each Cl will have -1. We have 3 Cl, right? So we have to put -3, which will be equal to 0, and X is equal to +3. So plus 3 is the oxidation state of this metal atom, okay, which is actually called as the primary valency, which is actually called as the primary valency. Now, what is this coordination number? The number of ligands, this is called NH3 is called as ligand. I will tell you what is a ligand later, okay? NH3 is a ligand here. The one which is present inside the curved bracket is called as a ligand. So it is fixed and the number is 6. So that 6 is nothing but the coordination number, which is called as secondary valency. Secondary valency is equal to 6, and that is the coordination number for this. Okay, clear? Shall I go for the next point? Shall I go for the next point? So I'll give some information about the different spatial arrangement also. Okay. So I am taking these two compounds. So do you remember this compound? So initially that Werner he did four compounds. He experimented with four compounds, right? So the last two had the same formula but different color. So you see here, these are those compounds. So both of them have the same formula with one Cl minus out, but the color is different. One is green in color and the other one is violet in color. Okay. So due to different arrangement of these molecules or ions around the metal, this is the metal and these are the molecules or ions. This is the metal, Cl and NH3 is the molecule. So due to the different spatial arrangement of these Cl and NH3 around the cobalt metal, we are observing two different colors. And we are saying these two compounds are called as isomers. Iso means same. Iso means same. Okay. So isomers means the compounds which have same molecular formula but different spatial arrangement of atoms. Okay. In this case, it is called as the compounds having the same formula but different structures or different spatial arrangement of atoms. Okay, so these two compounds are said to be isomers of each other. Okay, so here this is the coordination entity. The components which are present inside the square bracket is called as coordination entity, and the ion which is present outside is called as counter ion. It is called as counter ion. Okay, so I'll give you the structure of these two compounds also. I'll tell you why they have two different spatial arrangements. So let me take this. Cobalt is the central atom. And if I have two chlorine adjacent to each other and two NH3 adjacent to each other, then it is called as a cis isomer. Okay. And if I have cobalt here and two chlorine opposite to each other and two NH3 opposite to each other means it is called as a trans isomer. So around the central atom, around the central metal atom, the arrangement of ligands are different. The spatial arrangement of the ligands are different. So here they are adjacent to each other, but here they are opposite to each other. And because of this different arrangement of molecules, we are observing the different colors. Okay, both of them are different compounds. All right. So this is the components which are present inside the square bracket are called as coordination entity. The outside one is called as counter ion. Okay. So this is all about the experiment, the conclusion, and the postulates of Werner's theory. So is it clear? Shall I go for the next topic? Shall I go for the next topic? Okay. If you're getting any doubt in between, just feel free to ask, okay? Don't get scared. Yeah. So the next is the difference between double salt and a complex salt. Difference between a double salt and a complex. So what is a double salt? The salt which gets completely dissociated into ions. And complex means the compound do not dissociate completely into ions. They do not dissociate, and here they dissociate completely. Okay, clear? So I'll give you some examples. So I'll take an example for double salt first. So here I have a compound, and this compound is dissolved in water molecule. Okay, it is dissolved in water. And if it is dissolved in water, the cations and anions which are present inside that salt, okay, all these belongs to one compound. Okay, everything is a single compound. KCl dot MgCl2 dot 6H2O is the compound. And in this compound, I have potassium ion, which is K plus, Mg2 plus ion, magnesium 2 plus ion, which is a cation, and Cl minus ion, which is an anion. Cl minus, which is an anion. So do I have any other ions here in the compound? Only two, right? Only two cations and one anion. So if I'm putting the salt in the water, the salt is completely dissociated into cations and anions. Okay, but if I am taking a complex, let me take a complex. You see here, this is a coordination compound or it is called as a complex. If this complex is dissolved in water, it is producing cation and anion. You see here, it is producing K plus and FeCN6 4 minus. I am getting cation and anion, but inside the square bracket, I do have one more cation and another anion. Here Fe2 plus is the cation, Fe2 plus is the cation, and Cn minus is the anion. So that cation and anion is not getting dissociated. It remains in the water. It remains in the solution as such. So they do not dissociate completely into ions. So such compounds are called as coordination compounds or complex. Okay, clear for all of you? Clear? Can you able to differentiate between double salt and complex? All of you can able to understand, right? I'll give you some more examples also. Okay, so try to memorize the examples. So examples under double salt is more salt. So more salt formula is also given here. FeSO4, NH4 twice SO4H2O, and potash alum is the second example. KAlSO4 twice 12H2O. So in both of the compounds, the Fe2 plus ion, SO4 2 minus ion, NH4 plus ion, SO4 2 minus ion, everything will be completely dissociated. And here K plus, aluminium 3 plus and SO4 2 minus, everything will come out. But here in case of platinum complex and nickel complex, you see, so the platinum and Cl minus will not come out separately. In the same way, the nickel and CO will not get dissociated completely. Okay, so these are some of the examples. So you should know the double salt formula as well as the name. Okay, double salt formula as well as the name. Clear? So this is all about the double salt and complex. Now, next I'm going to give you the terminologies which we are going to use in the coordination compounds. Shall we go ahead? Are you all ready? Is everything clear up to this? Okay. So the first term that I'm going to take is coordination entity. First is coordination entities. Already in previous slide we have seen what is coordination entity. So the components which are present inside the square bracket, they are called as coordination entity. So inside the square bracket, what component we have? We have a metal, okay, we have a metal atom and we have the bonded ions or molecules. Okay. Zara, do you have any doubt? You have raised your hand, it seems. Do Sarah have any doubt? Okay. Yeah, I'll go ahead. So we have a metal atom and the bonded ions or molecules inside the blood. Okay, and we call that as coordination entity. So here is an example for you. So we have cobalt, which is a metal atom, and two different types of bonded ions, Cl and NH3 are here. And they both of them they are bonded with the cobalt, and we call this metal atom and the bonded atoms together as coordination entity. Okay, metal atom is surrounded by 3 Cl minus ion and 3 NH3 molecule. Okay, so the second term is central atom. So I have taken three examples for you guys. Can you tell me which one is the central atom in case of first compound? Take the first compound. What is the name of the central atom in the first compound? Very good. Cobalt. So cobalt is the central atom. Yeah, very good. And in case of second compound, iron is the central atom. Yeah, yeah. And in the third case, nickel is the central atom. So these are called as central atom and otherwise called as Lewis acid. Central atoms are also called as Lewis acid. So what are Lewis acids? The electron acceptors are called as Lewis acid. So they are called as Lewis acid because they accept electron from the bounded anions or molecules. Okay, so they accept electron. If I take this ion will accept electron from Cn. Nickel will accept electron from Cl and H2O. Cobalt will accept electron from Cl and NH3. Okay, so electron acceptors are called as Lewis acids. Electron acceptor means they are electron deficient in nature. That's why they are accepting the electron from the other. Okay, so Lewis acids are the compounds which are electron deficient in nature. Which are electron deficient in nature. Okay, so it is a central metal atom is a Lewis acid. Clear? Moving on to the third term. Third is ligand. So we have studied what is central metal atom. Now we are going to see about ligands. So these bonded ions or molecules which we are saying is called as ligands. Very easy. That's Cl, NH3, H2O, Cn we have seen. No? So those are called as ligands. Very easy. I will come to the classification of ligands later. Okay. So we will discuss the classification of ligands later. So don't worry. Now let me discuss the terminology alone. And one more thing I want to say here. Central metal atom is a Lewis acid, but ligands are Lewis bases. Ligands are Lewis bases. So why it is called as a Lewis base? Because they are electron rich in nature. So they will donate their electrons to the metal atom. So electron donors are called as ligands. Electron acceptors are called as metal and electron donors are called as ligand. Okay. Now the fourth term is coordination sphere. Coordination sphere and coordination entity both are somewhat similar only. Okay. So if I take this platinum tetrachloride complex, this complex together is called as a coordination sphere. And if I want to take some more examples, I can take this. So here K potassium, that K4 is a counter cation. This FeCN6 is a coordination sphere. So coordination entity and coordination sphere, both of them are similar to each other only. Okay. The fifth term is coordination number. So what is a coordination number? So let me give you one picture before going on to the definition. Okay. So here I have a metal. Metal is surrounded with 6 ligands. So I am going to say the coordination number is 6. And here I have a metal and I have only 4 ligands surrounding this metal. Now I am going to say the coordination number of this system is 4. So now can you define what is a coordination number? Can you define what is a coordination number? Can anyone tell me the definition of coordination number? Very good. Very good. Very good, Sneha Nahashri. Coordination number is defined by only sigma bond formed by the ligand with the metal. So the number of donor sites to the metal atom is called as, or the number of ligands attached to the, not the number of ligands attached, because we do have different types of ligands. Okay. Now here in this case, all the ligands are monodentate. Monodentate means they have only one donor site. So if the number of ligand is 4, coordination number is 4. If the number of ligand is 6, the coordination number is called to be 6. Some ligands will have more than one donor site also. Ligand will be 1, but the donor site will be 2. Okay, ligand will be 1, donor site will be 2. So in that case, number of ligand is not equal to the coordination number. I will come to those points later. Okay. So coordination number is defined by the number of sigma bond formed by the ligand with the central metal atom. Okay. Clear? Shall I go for the next? So all the terms which I have discussed so far, they are clear now for all of you. Do any of you have any doubts till now? Okay. Yeah. So the sixth term is coordination polyhedron. So what is this? The spatial arrangement of ligand around the central atom is called as coordination polyhedron. We have the central atom, we have the ligand surrounding the central atom, and the spatial arrangement of the ligand. So each ligand will be arranged in a different manner. Okay. So if I have 6 ligands surrounding this metal atom, then I will call this compound, or I will call this coordination polyhedron as octahedral. Okay. If 4 ligands are arranged in this manner, then I will call this as tetrahedral. The same 4 ligands, if they are arranged in a planar wise manner, it is called a square planar. Okay, it is called as a square planar. And if I arrange 5 ligands like this, then it is called as trigonal bipyramidal. So this is trigonal. Trigonal means this is the plane. So 3 ligands are occupying the plane. One ligand above and one ligand below. And if I connect all the 3 ligands which is there on the plane to the one which is present above, it will form a pyramid. And if I connect everything to the bottom ligand, again I will get one more pyramid. So I will have 2 pyramids. So both of them is called as trigonal bipyramidal. So that is the name of the structure. Okay. And if I have 5 ligands in this manner, what is this? So I have 4 ligands in the square plane. Square plane means you can take your notebook. Okay, so in notebook we have 4 corners, right? So let me take my mobile. So this is the mobile. So I have 4 corners. So one ligand is present above. So this is square, and if I connect the ligand which is present above this, I will get a pyramid kind of thing. So it is called as square pyramidal. It is called as square pyramidal. Clear? So here in both of the case, the coordination number is 4, but they are having different structure due to different spatial arrangement. The ligands are arranged in a space in a different manner. Here also both of them are having the coordination number 5, but due to the different arrangement of ligand, they are having different structures. So these are called as coordination polyhedron. If the coordination number is 6, then it is called as octahedral. Is it clear for all of you? Shall I go for the next? Shall I go for the next? Next, we will discuss about the ligands and its classification only. Okay. Any doubt from the 6 terms that we have discussed in coordination compounds? No doubt? Fine. So the next is ligands. Let's go for the types. Let's discuss the types. So as I have already told you, okay, actually students. So what I have said, yeah. As I have already told you, ligands are Lewis bases. Ligands are called as Lewis bases, which will give their electrons, which will donate their electrons. Ligands are electron donors to the Lewis acid, which are actually the metal. So the ligand will donate the electrons to the metal. So metal is a Lewis acid and the ligand is a Lewis base. You see the arrow? So two electrons are getting donated to the metal by the ligand. Okay, now this ligand has some classification. So the first classification of ligand is on the basis of charge. How many charge we have? How many charges we have? Can you tell me? Two. What are those two? Okay. What are those two? Very good. Very good. Sneha has given me the correct answer. Okay. Yeah. So it is classified on the basis of charge like anionic, cationic, and neutral. Okay. So if the charge is negative, it is anionic, and if it is positive, it is cationic. If the charge is zero, it is neutral. So now let's see each and everything separately. Okay. So let me go for the anionic ligands. So what are called as anionic ligands? The ligands carrying the negative charge is called as anionic ligand. Okay, so I will give you a list of anionic ligands now. All of you take these things in your notebook. Okay, I hope all of you are noting down the things which we are studying here. Am I right? I hope all of you are writing. No, Sneha is saying yes. What about others? Pallavi, okay. So if you are not noting it down, please try to have a notebook with you, separate notebook with you for chemistry and write down the things which we are studying every day. Okay? Yeah, yeah. Yeah, now we'll go for the list. We'll go for the list of anionic ligands. So I'll give you the symbol of the ligand and the ligand name. Okay? So the first ligand is F minus. F minus is called as fluorido and Cl minus called as chlorido. Br minus is bromido. I minus means iodo. Cn minus is called as cyanido or cyano. Both are correct only. And the next is O2 minus. It is called as oxo. OH minus is called as hydroxo. SO4 2 minus is sulfato. And NO2 minus nitro or nitrito. CH3COO minus is called as acetato. Okay. So in this 10 list, in the 10 symbol of ligand, the first five are very important. The first five from F minus to Cn minus, they are very important. Very important means they are the common ligands which we use in many coordination complex. Okay, clear for all of you? Can you able to find out one common thing which is existing in all the 10 ligands, anionic ligands? Can you find out that common thing and let me know? IDO. Yeah, everything is having O, right? It means all anionic ligands ends with, they have to end with the suffix O. Okay? All the anionic ligands should end with the suffix O in your nomenclature also. Okay? So you should memorize the names of the ligands also. So this is the list of anionic ligands. Shall I go for the next? Have you all copied? You can take the screenshot, you can take the photo, or you can write. Shall I go for the next one? Yes. Okay. The next is neutral ligand. Neutral ligand means the ligands carrying no charge. They are called as neutral ligand. Coming to the list, The first is NH3, which is called as amine. So here you will have to use 2M. Okay. If you using only 1M, then it will be wrong. You should not use one, single M. You have to use double M. Okay. So NH3 is called as amine. And the second thing is CO, which is called as carbonyl. Third is H2O, which is called as aqua. Fourth one is NO, which is called as nitrosyl. And the fifth is CH3NH2, which is called as methylamine. And also we have O2 called dioxygen, CH2CH2, NH2NH2. Very important ligand called as ethylene diamine, and it is denoted by En. Okay. And the next is PPH3, which is called as triphenylphosphine. And lastly, coming to cationic ligand, the ligands carrying positive charge is called as cationic ligand. Only very less cases of cationic ligands are present. The very common example is NO plus for cationic ligand. So we will have complexes, more number of complexes having neutral and anionic ligands. Cationic ligand containing complexes are very rare. Okay. So in this neutral ligand list, the first three, amine, carbonyl, aqua, and coming to this side, ethylene diamine. So these four ligands are very important. Okay. So you will have more number of complexes with these four ligands in the neutral case. Okay. Clear? Any doubt? The abbreviation used for ethylene diamine is EN. Abbreviation used is called as EN. Clear? Finished? Yeah, ethylene diamine is also the correct only. It is a common name. Ethane 1, 2. Ethane 1, 2 diamine is the IUPAC name. Ethane 1, 2 diamine is called as IUPAC name. So that ethane 1, 2 diamine name will be used in the IUPAC nomenclature of the compounds. That time I will explain. This is the common name. Ethylene diamine is the common name. We do have two different types of names, right? Common name and IUPAC name for all the compounds. So this is the common name. Clear? So before moving on to the next slide, I would like to launch a poll. So please, all of you, select your answers from the poll which I am launching it down. So once you complete, then we can go for the next thing. So finished, all of you? Okay. Okay, fine. So I want all of you to answer for these questions. Okay. Fine. So now let's go for the denticity of ligands. The second classification is on the basis of denticity. The first classification was based on charge, right? Anionic, neutral, and cationic. Second classification is on the basis of denticity. So what is meant by denticity? The number of donor atoms in a single ligand molecule to which it bonds with central atom is called as denticity. Number of donor atoms in a single ligand molecule. Suppose if I have a single ligand which is NH3, The number of donor atoms in this NH3 to which it bonds with central atom. So this is the central atom, central metal atom. This is the single ligand molecule. It has only one donor site. So this ligand is called as unidentate ligand. Okay. So the number of donor sites present in a molecule is called as denticity. So NH3 is having only one donor site. So at one particular point of time, it can donate only from that site. So it is a unidentate or monodentate ligand. Okay. Now I am going to take one more ligand. Ethylene diamine ligand I am taking. Okay, which is represented by En. So this molecule has two donor site. This molecule has two donor site. So CH2, CH2, NH2, NH2. So this is one ligand, but we have two donor site for this one ligand. Okay. So both the nitrogen can act as a donor. So one ligand is having two donor site. So it is called as bidentate ligand. I'll go for one more example also. Oxalate. C2O4 2 minus. C2O4 2 minus. So 2 minus we have. So the electrons are donated through that negative charge to the metal atom. So we have two oxygen donor atoms. So one ligand is having two donor sites. So these two ligands are called as bidentate ligand. Okay, clear? If I am having three donor site, what is the name of that ligand? If a ligand has three donor site, what is the name of that ligand? Tridentate. Very good. Also, this bidentate ligands are also called as chelating ligands. These bidentate ligands are also called as chelating ligands. So what is meant by chelation? So chelation means ring formation. Chelation means ring formation. So you see here, when they are forming the bond with the metal, they are forming a ring. So 1, 2, 3, 4, 5. So here ethylene diamine is forming a 5-membered ring with the metal. And here also 1, 2, 3, 4, 5. Here also the oxalate is forming a 5-membered ring with the metal. Okay. So this bidentate ligands are also called as chelating ligands. And the property chelation gives the stability to the compound. If a chelating ligand is present in the coordination complex, so that particular complex will be more stable in the solution, in the aqueous solution. Okay, keep this point in your mind. It is very important because in the examination they will give you 4 compounds and 4 options. Okay, and they will ask you to find out the molecule which is stable. So in that case, you have to use this chelating concept only. You have to check for the option which has chelating ligand. Chelating means the bidentate ligands or tridentate or some other polydentate ligands. Okay, you should not go for the option which has unidentate ligand. So those compounds are not stable, they cannot form the ring. Okay, so the compounds which are able to form the ring, they are stable in the aqueous solution. Clear? So let me go for the next. So when several donor atoms are present in one ligand, it is a polydentate ligand. Example is EDTA4 minus. The expansion is ethylene diamine tetraacetate ion. I will give you the structure, don't worry. So we know the formula for ethylene diamine, right? CH2, CH2, NH2, NH2. CH2, CH2, and NH2, NH2. This is ethylene diamine. And CH3, COO minus is called as acetate. This is called as acetate. And if one of the CH2, CH2, NH2, NH2, okay, here it is 2. If one of the hydrogen is removed from here and if it is replaced with the other one, then we get one acetate here. Okay. And also I have 2 hydrogens here, no? So replace both of the hydrogen with the both acetate groups. In the same way, replace 2 hydrogens from this NH2 also with the 2 acetate group. So what we will get? We will get 4 acetate with 4 minus charge. 1, 2, 3, 4. So it is called as ethylene diamine tetraacetate anion. Okay. Ethylene diamine tetraacetate anion. Now, all these 6 sites are donor sites. So all the 4 oxygen can donate through the negative charge, and 2 nitrogen also can donate because each nitrogen will have one lone pair. So the nitrogen also can donate through its lone. 6 donor site means it is a hexadentate ligand with 6 donor atoms. Okay, ethylene diamine tetraacetate is a hexadentate ligand. So this was one of the previous year question. Previous year NEET question, 2021 NEET question it was. Okay, EDTA is a dash ligand. Very easy, no? It is a hexadentate ligand. Okay. So the next type is ambidentate ligand. So the first classification was based on charge. There we had anionic, cationic, and neutral. The second is on the basis of denticity. So you monodentate, bidentate, and polydentate. And also I have discussed about chelating ligands in between. Now the last is ambidentate. Ambidentate means when there are 2 donor atoms in a unidentate ligand, then either of the 2 ligand can donate electrons to central atom. To be more specific and to be simple, I'll tell you the definition in short. Okay. One ligand having 2 donor site, but at one point of time, only one donor can act. Only one site can act as a donor. So I'll take an example so that you can understand it better. So take this NO2. So this NO2 has nitrogen as the donor site as well as oxygen as the donor site. But at one point, only one site can act as a donating site. So in the first case, you see only nitrogen is donating. Both of them cannot donate at the same time. That is what I want to say. Okay, but 2 atoms have the ability to donate. Okay, here oxygen is donating. So those are called as ambidentate ligands. When there are 2 donor atoms in a unidentate ligand, then either of the 2 can donate the electrons to the either of the 2. Either means only one at one time. Okay, nitrito N, and here it is called as nitrito O. So we do have some more examples. Thiocyanato S, where sulfur is acting as a donor in case of SCN molecule. And also we have NCS. Here nitrogen is donating. So it is called as thiocyanato N. Okay. And the third example is CN and NC. So here carbon is donating and here nitrogen is donating. Cyano, isocyano. Alright. So formula will be same, but the donating site will differ. Clear? Any doubt from this? So this is all about the classification of ligands. Okay, first is on the basis of charge. Second is on the basis of denticity. Third is on the basis of donating site. There also you can have the chelating ligands and ambidentate ligands. Okay. So first category, second category, and third category. So this is all about the ligands. And before this, we have studied about the Werner's theory. Okay. So we have done with the Werner's theory and ligands part of this lesson. The next topic is the nomenclature of coordination compound that we will discuss in the next session. Okay. The nomenclature of coordination compounds will be discussed in the next session for you. Okay. Any doubt from today's session? So do any of you have any doubt from today's session? Everything is clear? So just go through the notes and go and study the book or the materials which you have. Try to solve questions from the topics we have discussed. We will continue this in the next class. Okay? Okay, thank you so much. Take care. Bye-bye.